The topic of my talk is try to give you a relationship between a very geometric way to manipulate ellipsoids and some of the well-known means of the covariance matrices corresponding to the shape of the ellipsoids. So first of all, let me remind you what kind of geometric operation we're going to discuss, which are just the sum of two sets. So let's consider two sets which are just a subset of the Euclidean space in Rn, and probably you are familiar with the notion of the Minkowski sum and the Minkowski subtraction of two sets. So basically you take one of the set is fixed, and you take the other one and you translate to each one of the position of the first set, and you take the union of that. This is the sum, and for the case of the subtraction you will do the same, but with the intersection. Okay?
So it is y tilde p with index p?
It's just the translation. It's the position, the translation to the position p to each one of the locations. Okay? So in the particular case of the convex set, is close for that. I mean, if you take two convex sets, the result is a convex set for the Minkowski sum. In the case of the Minkowski subtraction of difference, just you need to have a convex set for the first set. I mean. So now what's happened with the case of the ellipsoid? Here you have two ellipses, and well, in fact you will obtain, of course, convex set, but they are not ellipsoid. So why it is interesting to consider how to obtain a kind of approximation to these convex sets which are still ellipsoids is because in many cases you would like to deal with this object. I mean, this geometric object, the ellipsoid, will represent also anything else, like typically a covariance matrix associated to that. So basically here we're interested on finding good approximations to this kind of convex set, which are the result or of the sum of the subtraction of two. So here the big one is the sum, and the small one is the subtraction between these two sets. Okay? So they are not ellipsoidal in general, these operations, and as I just told you, in many cases we need to have an output which is still an ellipsoid. So I want to use results which are from a very relatively well-known theory in control, which is the so-called ellipsoidal calculus. So this community, basically they consider solving problems in control and estimation theory such that the information is represented by set, and they will try to approximate the different steps in the optimization and all the stuff they need by approximation of ellipsoids. So basically all the results I will show you are proof from this community. My contribution is to relate some of these results to the means in covariance matrices, which are well known in information geometry. Okay? And the interest of this theory is, in fact, you don't need to compute first the Minkowski sum of the two sets and then approximate that subsequently by an ellipsoid. You have explicit expression of these approximations. So you can use straightforward all these expressions. Okay? So the motivation is done. So basically I already tell you what will be the goal of the talk. So let me start. Now I want to remind very briefly a few basic notions we need. Probably most of you are familiar with them, but at least to fix what I mean behind all these notions. So the first of them will be just the notation, how I will denote an ellipsoid, which will be just by this capital epsilon. So C here is the center, is the vector with the position of the ellipsoid, and Q is just the shape matrix defining the shape of it, which is a positive semi-definite real symmetric matrix. Okay, so you know about ellipsoid, all the properties, and also a brief reminder about the Hausdorff distance, which is one of the distances you can use on the Euclidean space for set. And basically you will take the two set and you will take a kind of, if we can reuse reinterpret the standard formulation of the Hausdorff distance using just the Minkowski sum, which can be rewriting like that. So you will take the smallest lambda such that you take one of the set, you compute the Minkowski sum with a ball of radius lambda and such that contains the other set. You do the same with the other one, and you take the smallest of these two scaling parameters. The ones will be included in the other. Well, this is very well known, this Hausdorff distance. But in the, I'm going to skip that. In the case of the ellipsoid, the Hausdorff distance has a more explicit expression where basically you have a term here on the distance which depend on the distance on the centers, and another one on the quadratic forms of that. And that will appear later, this expression. So Hausdorff distance. And the other thing I'm going to use, which if you are familiar with convex analysis and convex geometry, you are probably familiar with this notion of support function, which basically will give you a, for any, you can define that for any convex set. Here, typically, we will take all the possible direction on the space. You will not take all the vectors, but here it will be more as n minus 1. And basically, the super function for the case of the compact convex set is a real valued function. You have a one-to-one isomorphism for the case of the convex set, which has a few properties. And one, so this dual representation of convex set is very useful and extremely connected to Minkowski sum. They are very well-known and strong properties relating the superfunction and the Minkowski sum. And also about the connection is very interesting with the Hausdorff distance. So in fact, the Hausdorff distance of two sets, this is general, is just this kind of norm between the superfunction of the set. So in the case of the ellipsoid, if you remember the expression of the Hausdorff distance and you connect to the just I show you, you will obtain the superfunction of an ellipsoid is this expression. So with all these elements, I just have, I don't really have time enough to explain that. This is an independent result which is known from a few years ago, which is so let me give you at least a taste of this result. So basically, the idea is the following. Consider the space of the ellipsoids. Now we change the parametrization of the shape defining the ellipsoid. We will take P instead of Q, but it's just the square root of Q, just to avoid this notation, heavy notation, which appears later. So basically, we will consider on the one hand the spectral distance between the two shape matrices, here P. For two ellipsoids, we will define the spectral distance between the two ellipsoids. On the one hand, with this distance between the centers, this is just the L2 distance between the vectors of the position of the ellipsoid, and this one, which is just the spectral norm of the difference of the matrices, a very well-known norm in matrices. And we will have, on the one hand, this spectral norm. Now we focus just in the case of ellipsoids which are centered at the origin, so the position will be for both. So like that, we can remove this annoying term, but it's not a problem because we can consider the ellipsoid just at the origin. This is not a problem. So we have this expression of the spectral distance, and on the other hand, we will have this expression of the Hausdorff distance between two ellipsoids. So remember, this is a spectral distance between matrices, and this is a distance between sets in a very different setting, which using the superfunction of ellipsoid is writing by this way. So the main result of this kind of parentheses I am opening my presentation is the following theorem from 83 from this paper, which just will give you a relationship between the Hausdorff distance and the spectral distance. So what can be the conclusion of this theorem? And this is the rationale behind the rest of my talk. I mean, a kind of theoretical ground for the rest of the talk. That means we have the same considering the ellipsoids either from the set viewpoint using the Hausdorff distance or from the matrix viewpoint, the space of matrices, using the spectral distance, you have the same topology. So basically, you can deal in many situations with one or the other of the spaces, and you will obtain, from a topological viewpoint, similar results. So it's not surprising, it's well known, but in the very specific case of the distances, we have already this result. So let's come back to the beginning of my talk. Remember, we have Minkowski operation between ellipsoid, which is not anymore ellipsoidal, and we would like to approximate that by an ellipsoid. And we would like to have a good approximation, an approximation where we can control the degree of the approximation. Okay? So let me start by the approximation to the Minkowski sum. So basically, the idea will be, in order to define the approximation, we will fix one of the direction of the space. So our approximation will be good, will be in fact exact in this direction. And basically, we will have two kind of approximations. One which will be the internal, and another one which will be the external. So that means I have, this is the Minkowski sum of two ellipsoids, and we will have a family, a parametrized family of internal approximations and a parametrized family of external approximations, which will depend on the direction L here. And the idea of it is a good approximation is tied in the sense of the support function on this direction is equal from the Minkowski sum than for the two approximations. Okay? And if you remember the connection between the Hausdorff distance and the support function of the ellipsoid, that means in this direction, the distance between the two, the sum and the approximation is equal to 0. So according to the previous result, is exact on this direction. So basically, this is how we would like to find, how we like to define the approximation. So how they looks the approximation. So basically, in this theory of ellipsoidal calculus, they have all the proof for that. But this is how looks, for instance, the parametrized family for the internal approximation for the Minkowski sum for any of the direction L. It's quite simple. Basically, you need to compute just a matrix, a orthogonal matrix X, which is alienating these two vectors, which can be done by very simple linear algebra computations. So for any L, you know that will give you the ellipsoid, which is equal to the Minkowski sum in this direction. This is for the internal approximation. For the case of the external approximation, the expression is a bit different, but you have exactly the same kind of result. So just let me show you a few examples of how that looks. So our toy example from the beginning, in red, you have a few external approximations taking different directions, and in green, a few internal approximations, just using the previous expression with different values of this parameter L. Okay? So now, obviously, that is good for one of the directions. So we would like to have something which is, let's say, optimal in a certain sense, or in other terms, find the direction such that satisfied a particular constraint. So typically, as you can imagine, will be interesting, for instance, in ellipsoid, satisfying approximation satisfying, for instance, a size criterion, typically taking the one of the minimal volume or taking the one of the largest trace, which is internal or external. Okay? So this is something which corresponds just to take the previous expression, which depends on L. You take, for instance, the volume of that, you compute, you derivate that with respect to the direction, and you try to find the direction such that you will obtain the one which is optimal with that. For instance, this is the expression of the optimal ellipsoid external one having the minimal trace. Here we are more interested on the optimal one, the internal one, having the largest volume, so which is contained inside the approximation. So this is basically finding the right direction, and this is the expression. So, and as you can see, it's a quite, it seems quite complicated expression here. Let me rewrite just like that, and I will just come back in a minute to this expression. I am rewriting just in this different way. I will come back to that. Yeah.
Something, simple question.
Yes.
Suppose that Q1 is the identity. What is the simplest form? So, suppose that Q1 is the identity, and suppose that Q2 is simply diagonal. What does it give?
I will give you just in a few how we can interpret this expression. Well, in the case of in certain cases, if for instance you have allineated ellipsoid having the same orthogonal basis, things are quite simple. But I will just give you the interpretation of that. It will just give you a kind of mean between the eigenvalues, the arithmetic mean between the eigenvalues and the geometric mean between the eigenvalues for the case of the allineated ones. But let me move on that. So this is just to show you how that looks, the optimal ones. For instance, in green, you have the optimal ones in the sense of the volume, which is contained inside. And in red, correspond to the optimal one, the external one of minimal trace. So that to see how it looks for this example. Okay, and you can do the same with the Minkowski difference. I mean, you will have similar result where you can define again following the same definition of what do you understand by a good approximation according to a given direction, and you will obtain similar expression for that. Okay, well, I will not review all of them, which are quite symmetrical with respect to the other ones. Usually you have only a sign plus minus changing of that. Okay, and basically you will let focus us in particular in the expression of the external approximation of minimum volume to the Minkowski difference, which looks like the previous one except for this minus sign which appears here. Okay? So basically here we are dealing in all the previous result with geometric operations and constraints about in order to define the optimality about the determinant for the volume or the trace of the matrix. Okay, so now this is how I connect that with the means on the space of the symmetric semi-definite matrices. So I'm gonna just use two geometries to give you how they are related. Most of you are probably familiar with the geometry of the cone, or the symmetric positive definite matrices. And you know from this geometry we have the metric. We can define from this metric the geodesic connecting two of these matrices. And in particular, if you take the point in the middle of the geodesic, you will obtain the mean between the two matrices. So this is the expression of the mean of two matrices in this geometry of the cone. Okay, so this is in red appears, and this is well known in information geometry because instead of being the metric of the cone, is also using the Fisher metric, the one which corresponds to the distance, the geodesic, and the mean between two Gaussian distributions with zero mean, and using the covariance, so very well known in our community. There is another one which has been more recently studied in detail, which is the one related to optimal transport or quantum information. In this very interesting paper by Bhatia and co-workers, they were studying, they call that the Bures and the Wasserstein distance, also for positive definite matrices. And they study, starting from the distance, the corresponding geometry, sub-Riemannian geometry, and when they have the geodesic, again, they can define the mean between two of them. And it is interesting on this geometry to see how this mean between the two of them can be rewritten. In fact, it is a kind of mean average between the standard, let's say, Euclidean mean. So this is just the mean between the two matrices in the flat geometry, according to the Frobenius norm, which is this term which appears here, with 2. And this term which appears here can be seen like a deformation of the Riemannian, because it's not symmetric, it's a kind of deformation of the Riemannian one I showed you before. So in a certain way, this mean between the two, mean in this geometry is a kind of mean between these two things, which is a bit complicated here in the Riemannian part. So and now we come back to our ellipsoidal calculus and approximations, and in particular, let me come back to the expression of the optimal ellipsoid approximating internally the Minkowski sum, and the optimal ellipsoid in terms of volume approximating externally the Minkowski difference. Remember, they were these two expressions which appear here. And now I'm going to rewrite then just in terms of the mean between the two positive semi-definite matrices, which I defined as the Euclidean and the Riemannian just previously. So basically, you have this expression where the Minkowski sum, the approximation, the matrix shape approximation to the Minkowski sum is just 2 times the sum of these two guys, which appear here. And similarly, here for the difference, it's just the difference between the two there, which taking just the sum of these two equations, you can also say like that, the Euclidean mean between the two matrices is just 1/4 of the shape of the sum and the difference. And for the Riemannian one, it will be like that. So we have very explicit connection between what happened from a geometric viewpoint when you consider the volume as optimal defining these shapes, and a very particular way to combine an Euclidean and Riemannian metric, which is quite strange, this geometry. Well, I don't have time to go, I will not go into details, but only to be clear, this is not a kind of mean in a product geometry. I mean, we are not considering, or you will not obtain this result considering you are working in a kind of product manifold, sorry, which will be with a metric which will be the sum of the two metrics. So it's not at all that. So I will not go into details, but it's not at all that. So I have a few results to show you on images, but I think I don't have time for that. So how that looks basically, well, let me at least give you an example for this one. So basically, for instance, let's consider this is just an image with locally at each one of the pixels you have an ellipsis representing the anisotropy, the local anisotropy. Here you have the result of taking the Minkowski sum of each one of them, ellipses here, with this example which appear here. So you can manipulate, you can use this result also to manipulate images and to using the Minkowski sum, the Minkowski difference, to detect, according to the interaction between the two objects, this one and this testing one, the information of the image. I'm going to skip that. I don't have time to go that. Just the conclusion, basically. So ellipsoidal approximation to Minkowski sum and difference are the ones I were showing you are defined in terms of the Hausdorff distance, and which is a metric space which are topologically connected to a spectral space of the corresponding covariance matrices. This is the theory. But here we have a more explicit connection between the two, which is the expression just I showed you. Okay, thank you.